All right, let us begin. We're going to be looking at practice problem 4. In section 3.1 on page 66. Our objective is to plot a v-t graph for an elevator. We're told that the elevator goes through 3 different motions. The first of the 3 motions is that it accelerates at a positive rate of 0.5 meters per second squared for a total period of 2.0 seconds. Then, after those 2 seconds occur, it travels at a constant speed or velocity of 1.0 meters per second. It does that for a total amount of time of 12.0 seconds. Then finally, once it gets near its its final location, right? Here it's starting to move. Here it's moving at a constant velocity. Then it must slow down in order to stop at the floor it needs to stop at. Then it slows down at a rate of 0.25 meters per second squared. It accomplishes that negative acceleration over a period of 4.0 seconds. We see the total amount of time here is 2 seconds elapse, then another 12 seconds, then 4 seconds. So total time is 2 plus 12 plus 4, which is 18 total seconds. So our elevator rises. Here's our elevator. Our elevator rises for 2 seconds. Then it moves at a constant velocity for 12 seconds. Then it slows down, but is still moving upwards. This is just our acceleration vector. Here's 3, here's 1. It accelerates at first for a period of 2 seconds, holds a constant speed in meters per second for 12 seconds, and then it slows down at this rate for a period of 4 seconds. Now our objective is to graph on a velocity versus time graph the motion that's being described here numerically. In order to do that, we need a dependent axis and an independent axis. The first I'll draw here is my dependent axis, and here is my independent axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm going to draw it all the way across so I get to a total of 20 seconds. Now I need to label my independent axis. That's time as measured in seconds. Label my dependent axis, or my vertical axis, as velocity, as measured in meters per second. Well, what's the range in our independent variable? Well, we start at 0 seconds, and then eventually we get up to 18 seconds. So I'm going to have each of these ticks. Each of my grid squares will represent 1 second. Each of these will represent 2. Oh, this should be 18. There we go. Now, the velocity starts at 0 and ends up at some maximum. See how we accelerate and get up to this speed, this velocity, and then we slow down back to 0. So we'll say here is 1.0 meters per second. Now, starting at an initial velocity of 0, we can put our position, our velocity at the origin. Over a 2-second period, we accelerate at this rate. So over 2 seconds, we get up to over 2 seconds, or for each second, right? Because by 0.5 meters per second squared, we also mean 0.5 meters per second for every second, for every 1 second. Meters per second, right? These two are synonymous. So in the first second, what should be our velocity? Well, our velocity would have increased, since we have a positive, would have increased from 0 up to 0.5. So we'll say we'll get up to here. And then after another 1 second, we're finally up all the way to 1.0 meters per second. Now, if I analyzed the slope of my graph so far, again, this is a velocity time graph that so far describes the first movement that my elevator has made, in that it accelerated over a 2-second period. Here's my 2-second period. We would see that the slope of this line, is equal to the change in my dependent variable over my change in my independent variable. What is my dependent variable? We're looking at velocity, so the change in velocity over what is my independent variable? My independent variable is time. Change in velocity over change in time, that is average acceleration. So if I wanted to immediately be able to draw this, I would know that over this period of time, so from 0 to 2 seconds, I need to draw a line that has a slope of 0.5. Because that slope of the numerical value of this slope that we see here, the numerical value of the slope is 0.5. That describes movement 1. What about movement 2? Movement 2, do we see an acceleration? In other words, do we see a change in velocity? Our problem tells us that we move at a constant velocity for these 12 seconds. So we get from 0 up to 1 meter per second, but then once we get to 1 meter per second, we stay at that speed, at that velocity, for 12 more seconds. So we go from 2 seconds to 12 more seconds, which gets us to 14 seconds. So from time equals 2 seconds to time equals 14 seconds, we're traveling at a constant speed of 1.0 meters per second. Constant velocity that is positive, and hence we're on the positive part of the dependent axis. That's for a total time of 12 seconds. Now the time that we're at is 14 because we had these first 2 seconds that were the acceleration with the slope. Notice, what is the slope of this line here? The slope of this line is 0 because the acceleration at this point in time is 0. In other words, there is no change in velocity, so there is no slope, so there is no acceleration, right? Now, what do we see for the last 4 seconds? So from 14 seconds until 4 more seconds, when we're at 18 total seconds, we see that for every 1 second that passes, we have a decrease in speed or velocity of 0.25 meters per second. For every 1 second, there's a decrease in velocity of 0.25 meters per second. Well, if I accomplish that change in velocity over change in time, because this is a value of acceleration, so if that's my acceleration, and I know that average acceleration is change in velocity over change in time, well, if I solve this equation very quickly for change in velocity, I see that I can find the change in velocity that I've accomplished if I just multiply whatever change in time occurred by the acceleration. Well, the change in time or the amount of time that this third movement took place was over a period of 4 seconds. 4.0 seconds. The acceleration that I underwent was negative 0.25 meters per second squared. Notice the units I end up with is I lose one of the seconds, right? This was seconds squared, so I had 2 seconds, or seconds times seconds. Now I only have seconds. Still have meters, still have 1 second left. So I end up with a change in velocity of negative 1.0 meters per second over that total period of time. So in a 4-second period from 14 seconds to 18 seconds, which would be a change in time of 4 seconds, I went from 1.0 meters per second and I lost 1 meter per second. In other words, if I look at my final velocity minus my initial velocity, that's another way of describing change in velocity, right? Just as we say change in x is final at x minus initial f. I know that if I don't know what my final velocity will be, but I do know what my initial velocity was. It was 1.0 meters per second. I can solve this very simply and see that my final velocity must be 0 meters per second. So after 4 seconds of time passes, so from 14 to 18 seconds, I end back up at 0 meters per second. Which makes sense in terms of our problem, because in an elevator, think of any time you're in an elevator, you get on, it's not moving at all, then all of a sudden it speeds up. Here's where it's speeding up, it's accelerating, you feel heavier, and then it gets to its cruising speed, if you will. So it keeps moving at a constant velocity for a period of time until it gets close to the floor that you ultimately need to get to, and then it starts slowing down. Notice here, this third movement here, if we took the slope of this line, we'd see that it's our change in velocity over change in time, which again is our acceleration. This would be our acceleration here for movement 3. So the slope of this line, notice how it's not as steep as this line, because the slope of this line, its steepness, well, should be twice as steep because it's twice as large. This was 0.5 meters per second squared. This was negative 0.25 meters per second squared. Notice also this line here for movement 1 has a positive slope because we have a positive acceleration. Here we have a negative slope, or from left to right it's going down because we have a negative acceleration. This is the velocity time graph that explains the velocity of our elevator as it goes through an initial acceleration to get up to speed, holding a constant speed, and then slowing down with a negative acceleration until it gets to the floor. After 18 total seconds, we would say, well, they went from the first floor and they made it to the 3rd floor after 18 seconds. To touch back on this again, the math I did here, was I simply said, well, the change in velocity is defined this way. With this equation, we just rearranged the acceleration equation very simply, end up with a change in time times our average acceleration gives us the change in velocity that our object goes through. In this case, our object is the elevator. Plug in the numbers for a change in time. The number or the measurement for average acceleration gives us the change in velocity must be negative 1.0 meters per second. I don't know what the final velocity is, but I do know my initial velocity. That was 1.0 meters per second. Right? That's what I was going before I went through this deceleration or this negative acceleration. So I can plug that value in, and I quickly see that if I just add this to the other side, right, then I end up with just 0 meters per second. In other words, negative 1.0 meters per second plus 1.0 meters per second gives us 0 meters per second, and that's what our final velocity would be.